All right. Can you guys hear me? Is the microphone on? I'm a little busy at the moment. Can any of you tell me how I can have this little butterfly floating in the air? Anybody tell me? Just shout it out. Yes. Static electricity. What would you say about the two charges, the one on my little stick and the one on the butterfly? Are they the same or are they different? Why do you say they're different? Because they're repelling. All right. My trusty assistant, Xander, does not have the same plastic wand I have. What do you have? Plastic and what? Felt or wool. Let's see what happens when he gets close to it. What's happening to his wand? It's attracting. Why do you think it's attracting? The opposite charge that we have that is there. And in fact, let's see if you can hold it up with your oppositely charged. Whoa. All right. We will take that out of, oh no, I've relit it. We'll just let it fall to the ground there. Thank you guys very much. So the question comes, Xander, if you want to come back out here, the question comes, we said we had like charge on the butterfly, my rod, and he had the opposite charge. But which one is positive charge and which one is negative charge? How do we define positive? Anybody know? What'd you say? Lack of electrons, that's fantastic. All of you are blessed with the knowledge of an electron. No one who discovered everything we're going to learn today had any idea that there was such a thing as an electron. Does anybody know how we define positive if we don't know anything about electrons? What's that? Well, if you don't know about electrons, we don't know about absence of electrons. We don't know anything about electrons. So the answer is, we guess. And the person who guessed was Benjamin Franklin. And so, to figure out whether or not this balloon, see if I can launch it again, is positive or negative, Benjamin Franklin said, rubbing a silk cloth on a glass rod, the glass rod is positive. And that is how positive is defined. All right, so let's just launch the balloon, and we'll find out. Is it attracted to, what is the balloon? If it's attracted, is it attracted to it? Yes, it is. So the balloon must be negative. All right, so now we have defined positive and negative. It's all based upon the glass rod. Now, you probably are wondering, what is this crazy guy doing rubbing things together? And one of my students did this awesome molecular model. There we go. This is all from toys my daughter had in the garage this morning. So we've got our molecule, and what we're going to do is we're going to rub it, and we're going to tear off an electron. Now we've got an electron, negative charge. We've got a positive charge. This is called triboelectric. We're using friction to separate the charges. And that is the first place that we, as human beings, started to learn about electricity. Can anybody tell me where the word electricity comes from? Yes. The word electron is absolutely correct. We just have to realize we didn't know anything about electrons, but it's based on the word electron. So what does the word electron mean? Dr. Pavlidis, can you help us out? The Greek gentleman here.
What was that? Yeah, they got us. Yeah. Well, I think it was like thunder and current and so on.
So there is amber. It's hardened sap, I think, that comes out of a tree. And in ancient Greece, that was called electron. And an amber was a piece they would rub something against to create a static charge. And so that is where electron comes from. While we're on it, does anybody know where magnetism comes from? Yes. The Earth indeed has magnetism. That is a correct answer. Anybody know where the word magnetism comes from? Anybody knows what the first magnet was? What?
A compass.
A compass was one of the first magnets, but what did they make the compass out of? Any of you heard of a lodestone? A lodestone? You've heard of a lodestone. Excellent. Yes, do you know where the first lodestone was found? I'm going to get this wrong, but I believe it's the island of Magnesia in Greece, in that area. So the lodestone was a naturally occurring magnet. That's where it was found, so magnetism is named after the place. So I hope now I've revealed a little bit of the lack of mystery on where these things come from. They come from standard, ordinary places. So I learned how to do all this on my scholarly leave at the Royal Institution in London. Michael Faraday was a professor there for almost 45 years. The Royal Institution was the YouTube of science in the 1800s. It was the only place you could go to hear public science discussed, and everyone went to it. When I say everyone, if you think of anyone alive in the 1800s as a scientist, they went there. I wish I had the picture of Tesla's bench when he was there. It looked very much like this. And so today we are going to do the style of education that the Royal Institution does and that they did during the 1800s, which is one of demonstration and showing. For two reasons. One, a lot of non-scientists came to the lecture. Two, it's a little bit more engaging than me sitting here doing some PowerPoint or on the document reader typing things out. So I just wanted to show you, people from my class already know this. I bought myself a birthday present this year. Let's see if we can zoom out. So this is, if I can get a focus, I'm not a French person, Manuel d'électrique dynamique, and this is by Ferrand, that's not how you pronounce it, but he's French. And he wrote the very first book in 1823 on electrodynamics. And how did he teach it? Well, let's just go to the back. He taught it, by the way, this is the original book from 1823. He taught it, get it out there, by building a table and having about 100 different experiments he would do on the table to explain to you all of the knowledge of electrodynamics. So we're following in their tradition there. All right, so let us move forward. I have lots to show you today. Okay, so we talked about triboelectric. You saw me rubbing the stick with this. I'm going to rub this plate. This is a styrofoam plate. I'm going to rub it. And now it's charged. But how do you know it's charged? Well, the reason you know it's charged is because Xander here was kind enough to go and build us some charge wands. So let's see if I can turn, okay. See if we can get it. It's blue, right? So I rubbed this on the plate and I got it to be blue, okay? Now I'm gonna take a very magic material, okay, a sandwich bag, and I'm gonna try it on the same one. I might have to do a different one, but let's try. Okay. If I'm lucky, it still goes blue, so we need another plate. Let's get another plate over here. The problem here is once you put charge on it, it's almost impossible to get it off. There we go. So I'll put this here, my plastic bag. Okay. I'm going to see if it works first on my end. And it is not working for me. Will this work for this one? It's not working. It's not working. Hey, see the red? Quick, quick, quick. Take a look at the red. Thank you. Applause now. Thank you very much. Thank you, thank you, thank you. Needless to say, there's a reason I use the rabbit fur and not the plastic bag to demonstrate that. So what you saw there was that with the same item, depending upon when I rubbed it, either electrons came off of this or electrons came off my bag. And in fact, they've gone through and rubbed everything against everything, and they have a nice little tribological series that says if you rub this against this, that one will get the electrons, or this one will get the electrons. Okay, so now we know how to rub things together. We actually know things that work really well. By the way, cat fur is really, this is actually rabbit fur, is really, really good. Leather is also very good. So they learned that leather and glass, plastic, and this fur work really well. Okay, so now we are at understanding how we can get some charge. Now, what I'd like to do is talk about an important concept called induction. And to do this, by the way, this beautiful balloon, can anybody tell me what this balloon is on this side?
Thank you.
Oh, come on. Okay, how about this side? Plus, minus, okay, we got it. So let's just bring our balloon out front here, okay? Now, by the way, I chose this balloon because it's made out of mylar, which is metallic, so charge can move around on it. So I'm going to charge my stick, and what happens to the balloon? The stick is attracted. Is there any charge on that? Did I put any charge on that? No. The MIT professor taught me that. You put it against your cheek. It makes it seem real that I've taken all of the charge off. There's no charge on that balloon, unlike our butterfly. Now I wonder, what if I used a different charge? What if I used Xander's charge? Is it going to attract or repel? What do you guys think? They both attract. This one lasts because it doesn't have as much charge. What is happening is when I put this, I think it's a negatively charged stick here, the positive, don't fly away, the electrons, they repel onto the back, and the front becomes positive, and then positive gets attracted to my negative stick. Now, if you don't believe me there, which quite frankly I don't think you should, we can do it with the ever popular demonstration of a Coke can. You can do this at home. Coke can is metal. What should the Coke can do when I put my stick near it? See if I can get it to roll over again. Ooh, did you notice that lights up? That's kind of cool. Now, I've told you this story about charge goes to one side and the other side becomes oppositely charged. Did any of you see electrons move from this side of the balloon to that side of the balloon? Okay. Did anybody see that? Why do you believe me? How do you know everything we've taught you isn't a giant hoax? The PowerPoints, the exams, the books. We just made it all up for you guys. So I encourage you to say, hey, wait a second. I don't see how that could be real. I don't understand. Can you prove it to me, Professor Ricketts? And I think I can. At least I proved it to myself because I wasn't quite convinced. This is a device we're going to talk more about later. It's a Van de Graaff. It's going to generate an electric field. By the way, an electric field I got from just charging this up negative. There's an electric field around it. Don't ask why. Just say, yes, I got that. All right. So I'm going to put two wands. Can you get a close-up on these? I'm going to do them this way. What do you guys see on the wands? Okay. Right. So they're touching. So if I put them next to an electric field, I told you if this is negatively charged, the electron should run over here, and this will be negative, and this will be positive, right? Let's just see what happens. By the way, these are positive, so I think it's going to be the opposite way. Okay, so I put them close up, and now watch what I do. Ready? Ready? I separated them. Xander, can you help out with the charge wands? Yes. Just up, if you can go up front. They seem to be overly sensitive. You may have to do this again, so if you can get a charge wand. Just give me one of them. Not that. That's good. So that's red. No, it's too much. No, can you touch the Van de Graaff to short it? This one. Ha, that was fun. Did we get a blue light? Yes, look at that. Red and blue. I proved it was induced because I said it was, and then I separated them. And now you can see I have my two separate colors. If I bring them back together, there's no charge. Okay? So this should show you that indeed all the electrons ran to one side and the other side became positive because I separated them. Now, have some of you needed to go to the restroom? Do you feel like some sound in the room has been going on for quite a while? This is not a pause for that, but is this working, Xander? Yes. Okay, awesome. So the first thing people did is they said, can I use induction to create charge? And they, in fact, do over here. So what we have is we have water is flowing down, and you probably notice the water goes down and then it forms into drops. Okay? Imagine these are my water. If I charge up this little coil here, I'm going to get a little separation of the charge in the water. And then wait for it. What happens when the water falls? The drops separate. It turns out the drops that go down to the bottom have this charge, and the positive charge stays up in the little nozzle there. So we keep on having drops of negative charge, dropping down, dropping down, dropping down. And if we can get a zoom in right here, you can come in front. We might need to do it so you can see it in front. So this is an electroscope. And what I've done is I've connected it to the bottom one. And we should see the foils start to separate. You see them separating? It's because it's repelling the same charge. And then you see it pop. Now what I'd like you to do is look at the very front. I have put a light on the very front. Let's see if I can dim everything. Will I get everything? I'll let you try. Can we see the light flash? Right here. Soon, soon, soon. Come on, there, did you see that? You leave it on there, I'll explain why it's happening. So what we've done, you zoom out a little bit. You see the two little steel balls? We put the steel balls far enough away that we have to build up a few thousand volts for a spark to go across. And when the spark goes, that light turns on. So we are generating several thousand volts on each side just by letting gravity separate our induced charge from positive and negative. This is the Kelvin water dropper experiment. If you ever go to the Royal Institution, the following thing you will hear over and over again, and this was first demonstrated at the Royal Institution in 1800. All right, can we get the lights back up in the front? All right, so that is one way that we can generate electricity, a few thousand volts. Another way we can do it is also through induction. And I've got a little light here, there we go, okay. So what we're gonna do is, I'm gonna take my rod here. So, I'm gonna charge up my plate. See if it's charged. I got a blue light, that's awesome. Now I'm gonna put this metal plate down. Now, you can't hear me thinking, ouch. So what I've got here is a little light. So when I touch it there, the spark's gonna go across and you should see the little light go. So we can get it down, let's see if we can get it. You guys see that? There we go, okay. Now, let's go see, sometimes I have charge on me. Let's go see what the charge is. What's happened? The charge is gone. Well, I had charge on the bottom. It repelled an equal amount of opposite charge on the top. I touched my finger so it could fly off into me. And now I have equal and opposite charges, one on the plate, one on the metal. Do you believe me? Why would you believe me? This is the theory. So what I'm going to do now is separate the two. That is blue. Okay. This is one of the things I like about Victorian demonstrations is I put them back together. Am I going to see a charge with my wand? Not because there isn't charge, but because the charge cancels. Get off away. There's our red. There is our blue. So now I've transferred charge. That's pretty cool. Ah, here we go. I got this little thing here. Now I could go and touch it. I don't know if you heard it. It was a little spark. Now I can go back here. We're going to do the little light again. You guys see that? Now I've just added more charge here. And now I've gone here. And I can go back here. And I can keep on touching. Can you maybe kneel down or something just so we can get some? There we go. And I can keep on going back and doing, this is called electrophorus. I basically create a static charge and I can keep on inducing charge by touching it and then I can transfer it over to here. And that is one way that we can generate voltage. And if we just want to verify we can generate voltage, I've got this handy duty electrometer and we can see we've got an electric field on that little can that is there. Now, this is great. But there's a little bit of a limitation here. And what I'm going to do is I'm going to show you that limitation with my Van der Graaf. I will explain how this works later, by the way. That was my birthday balloon, in case you're wondering. Right now, this is just generating some charge. And what I'm going to do is I'm going to set up my electrometer on this can, okay? So I've taught you we can create charge. Now the question is, can we just do this forever and create 1,000,000 volts? And the answer is going to be no. Touch this, and now I'm going to zero this out. And I can't, come on. I can't, just so you know, I can't turn it anymore. Okay, I'm not sure why we can't zero it out. What happened? This is wild.
Move the plate as well.
Oh, thank you. Should still. Genius! Genius! That plate had so much charge, this couldn't zero out. We did that on purpose, by the way. It was a learning experience. Okay. All right, can you guys see this top? You may need to stand up for this, so you can go down and see this. Okay? So what I'm going to do is I'm going to turn this on, and I'm going to say, my job, I'm a little technician in 1825, is to charge up this can. And so the question is, can I do this forever? So we're up to 2. Okay, we're about 2.8, 3, 2.9. You see, we're not able to get it much above 2.8 or 3. I can't get it any higher. Can anybody tell me why? Transferred charge from here to here, yes.
Is the charge split between the wand and the device only get half the charge?
It is true that some of the charge goes on the wand, but this keeps on, if this wasn't generating charge continuously, you'd be right, but this is generating charge continuously. So why can't I put more? Yes? It only has so much surface area, which means it can only take a certain amount of electrons, which means it only can have a certain potential. Do you think the potential of this and this can be higher? Well, let's see. Let's bring out our little demo here. Forgot about this one. Do you have the siphon hose anywhere close? All right. I think we used it to prime. All right. We will... it's a clear hose. I thought we used it to prime the... All right. All right, we will come back to this really important demonstration. No, actually, we need it now. Sorry. It's really important because we're going to do it now. All right, so what I'm going to do is I got 2 containers. And this is cherry juice. Just making it sound pleasant because Xander has to siphon it. Okay, go ahead. Good luck. Look the other way. There you go. Oh! Okay.
Get a little water in this one.
Yeah. It was my fault. Are you capturing all this on film?
Oh, gosh. We don't need records of this.
Yes. All right. Awesome. All right. Thank you. Let's give Xander a round of applause. Excellent job. It's a bear being a technician in 1825. All right. So I'm going to keep on adding charge to here. I can transfer it right. But is this one ever going to go any higher than that one? No. So this is a fundamental problem that we're going to have to solve sometime today. And in fact, we will. And I actually want to skip ahead, for the interest of time, directly to how we do that. All right. I'm going to explain these, and then I'll come back. Can we get these lights on? Nope. I think it was that one. Nope. These 2 in the front. I think it's these. Oh, whatever you just did was perfect. No, that wasn't what we wanted, but that's okay. Not that one. Not that one. That one. Nope. Try it. All right. If anybody back there wants to try some stripes to get this out, that would be great. Oh, whatever you just touched. Was that you? Did you guys hit a switch? Can you try it? Can you try a switch? There you go. Thank you. Awesome. Great. All right. Young lady, what is your name?
Gloria.
What's that?
Gloria.
Gloria. Gloria, can you come up here? Okay. Gloria, what do you notice? You can stay in front. What do you notice about these two silver balls?
One has a hole and one does not.
One has a hole and one does not. Thank you very much, Gloria. That is excellent. That is the key to understanding how this works. You can sit back down because we're going to get lots of sparks and don't want you to die. So, I'm sorry, did that come out loud? sorry about that. Okay, so if we go on YouTube, this is a Van de Graaff generator invented by Professor Van de Graaff at MIT to do particle acceleration. Anybody been to the Boston Museum of Science? They have a giant Van de Graaff there. I didn't know this. It is the Van de Graaff machine. It is the one he built in 1920s, and they still have it in action today. And here's what it is. If you go on YouTube, they're going to tell you a bunch of stuff. Can you zoom into the bottom? Can you see this little belt? Let's go to this one over here. This is a bigger one. So you can see there's a belt. And the belt's going to rub against a little piece of plastic. And they're going to tell you that we're going to create charge, and the charge is going to go up like a conveyor belt. So it's going to continually do charge. It'd be like if I was continually rubbing, and a little conveyor belt brought it up to the ball. But Gloria pointed out something very important. Do you notice that the charge, where does the charge go? Does it go on the outside or does it go on the inside? Where does the Van de Graaff, a normal Van de Graaff, where is it sticking the charge? The inside. That is the magic of a Van de Graaff. So what I've done is I've simply pulled, this should go on this way. I've just pulled it, and this is just to hold it on, and I'm going to put this on here. So the only difference between these two Van de Graaffs is this one's going to put the charge on the outside of the ball. This one's going to put the charge on the inside of the ball. Okay? And let's go and see what kind of differences we get. So I'm going to turn this one on. And I can already feel the power. Can we turn down all the lights? And whatever that magic light that did those, was that in the back? One more light. Okay. Okay. Kind of hard to see. Can you guys see it on the? Okay. So I can go, depending on where I go, I get about an inch on this one. Now what I'm going to do is I'm going to turn on this one. And notice, I get maybe a couple millimeters before I can get in. You guys see that one? Go to this one over here. See those big ones? See that big spark? By the way, I don't know if you can see it. There's a force on my hand, and it actually moves every time I get a spark. Okay? And so what's going on here? Why does... Oh, yeah, the charge wands have gone crazy. Let's turn the lights back up. Why is it that just changing the ball makes all the difference in the world? Well, remember this experiment here, if you want to get out of the way so people can see. The experiment here, right, we could only raise this to the same potential. Well, when we're on the outside, it's the same thing. We're just taking charge up, and all we can do is charge this up to the potential that the charge can create on here. This can go higher. And the question is, why? So I want to do a little experiment here. We're going to come back to our charge wand and turn it back on. Okay, let's see if I can. Sandra's taught me to like touch everything around to make sure it doesn't have any charge. There we go. Okay, it must have picked up some charge. Okay, so we're at 0. So now what I'm going to do is turn on this guy. That's going to be too much for it. Let's see if we can turn it back here. Ouch, that hurt. Okay. Zeroed out, okay. So now I'm doing just like I did before, and I'm transferring charge by hand. Have any of you heard of a Faraday cage? Is there any electric field in a Faraday cage? If I put an electron inside of a Faraday cage, any idea where it goes? What's that? Goes to the outside. So here I'm transferring directly to the outside. The outside, I can't charge any more charge because I have a certain potential on here. This is the same potential. I'm not transferring any charge. It's exactly like this. Now, what am I doing? Where am I putting the charge? There's no potential inside, so I can just keep adding as much charge as I want. It is not like this. On the outside, it's like this. Do you have the bucket ready? Yes. Inside of a Faraday cage, I'll let you do this, the potential is going to be such that it's an effectively zero, and we can keep on adding charge as much as we want. So the Faraday cage lets all the charge on the inside go to the outside, so I can continue filling up here and just continually adding charge over and over again. So the magic of the Van de Graaff machine is Faraday's cage. It's putting the charge, ouch, you saw that, inside of the dome. And these are one of the magic things that I think aren't normally very well explained. Okay, great. So that is how we do a Van de Graaff machine. And I brought a big Van de Graaff machine. You ask why, and the answer is just because it's fun. All right, we don't need this on anymore. See what we can get here. Oh, come on. That wasn't very good. Anybody tell me why the bigger Van de Graaff machine might have a higher voltage? Why? Because it's bigger. That is exactly correct. That is exactly correct. Now, you noticed over here that I said inside the Faraday cage I could put as much charge as I wanted. I can until the voltage difference or potential difference between the sphere and the air is so high that the air breaks down. And so if I want a higher potential, I need to have a bigger sphere so I can hold more charge, because I can't get a higher charge density because the air will break down. And that is my limitation. Now, I told you we might get to 1,000,000 volts. I told you I might live through the lecture. 2 of those might be true. So, in high voltage, it's approximately 30,000 volts per centimeter. So that's about 5 centimeters. So 150,000 volts. That's how we measure it. And actually, at some point, that was how they measured voltage. It's a little bit different depending upon the moisture in the air, the shape of my domes. But we got about 150,000. Over here, we had a few thousand. We're going to skip that one, and we're going to move straight to the next one in the interest of time. Have you set that up for 12 volts? Awesome. Excellent. Excellent. And could we get a couple of paper towels over here? I'm going to clean up the cherry juice. Okay. All right, how many of you recognize this? Can somebody tell me what it is? Yes. It's an ignition coil from your car. Now, once again, magnetic induction was first demonstrated at the Royal Institution. It gets old after a while, I agree. Michael Faraday discovered magnetic induction at the Royal Institution. And that is how we get to our next level of voltage. And what it is that we're going to do is we're going to pass a current through a small coil. It's in there. It's stuck in there. So what we do is we're going to put current through a coil, put it next to a coil with thousands of times more turns. And when we disconnect the current through this coil, energy's got to go somewhere. It goes into this coil, gets multiplied, and we get a huge voltage that breaks down the air. And so I'm going to demonstrate this just by, hey, you got this all set up. This is pretty cool. Can we turn the lights off? Let me just turn it around so you guys can see it a little better. That's too much. You guys see the spark? Get that? Can you move away just so people can see on the outside there? So all we're doing, and this is exactly how your car works, is we put electricity through a small coil, we stop the current, the energy has to continue, and that energy then causes it turns with thousands of times more to go to a high voltage and spark. I just did this because it's fun, but that's not really cool because if anything's better, a bigger spark is better than a smaller spark. Okay, this is the one thing that you've learned. So I'm going to take away our that was not fake. I told you I might not survive. So what I have here, we turn the lights up real quick for a second. So what we have here is a Ruhmkorff coil. And remember how I said, do you believe me? I never believe anything, so I bought 2 of these and I took one apart. So what it is inside of here, it's got a primary that we're going to put current through, and then this secondary on top. There's actually 2 of them connected in series, has thousands and thousands of turns, and when it disconnects, there's a transistor that connects and disconnects the current. It's going to go to 5, 10, 20, 30,000 volts across these. Now, the reason you can't see the coil is with those kind of voltages, the windings would break down, so this is actually encased in oil. So that's why it's inside. How do I know it's encased in oil? Because I took it apart. And if you go to a lab bench, we have a very nicely polished lab bench that has been recently oiled, okay? All right, so we're going to turn it on, and we're just going to see how high is this a musical interlude? I'm just kidding. See what we got there. All right, so we're able to generate, that's a good 5 or 6 centimeters, so 150-ish thousand volts. That's pretty good. And I can make it stronger. You know what? Let's just have some fun because we're here. Let's just turn it there. Yeah, that's pretty cool. Now, one of the reasons that we have to have such high voltages is because we have to break down the air. So we've got the air in between us. What I've got here, if we can turn the lights up real quick, is I have a vacuum pump. And so I have a little connector connected to this side's connected with the red lead to the outside. All I'm going to do is pump all the air out. And what you'll see is this is a good, I don't know, 15 centimeters. Can't get 15 centimeters here. We're going to pull all the air out, and that'll allow the electrons to leave and go down to the bottom. And if you ask me, are the electrons going from the bottom to the top or the top to the bottom, I have no idea. Okay? All right, so let's give this a go. So now this is a lower impedance path, and we have a direct line of charge flowing from the top to the bottom. And that's really cool. And Ruhmkorff, by the way, he did not invent this idea. This was invented by Joseph Henry in the US, invented it around the same time as Michael Faraday. Ruhmkorff was an instrument maker, and so he made the best coils. So everyone refers to his name as the person who makes the best coils. So now, in the late 1800s, this was the absolute best thing you could ever build for high voltage. And they came up with one of the most amazing demonstrations. I'm not sure we can capture it on camera. What I'd like to do when I ask is, you guys in the back and you here to try to turn off all the lights and to see if we can see it when I ask. So I have here a uranium glass. So back probably before it was dangerous, the way you made green glass was you put uranium in it. And so I picked this up at CVS this morning. And I did not pick it up at CVS. Anybody wondering that? All right, I got to let this out. Can you let me know when that dial goes to 0? Okay. Okay, all right. So what I'm going to do is I just have some tin foil. We call it aluminum foil. In the UK, they call it kitchen foil. By the way, the reason it's called tin foil is because they used to make it out of tin. And that is what Michael Faraday used. In his notes, he talks about using tin foil. So all I've done is put some in the inside, and I'm going to stick my little ball of the end of my conductor right inside here. And everything else is the same. I'm going to tighten that back up. I'm going to turn the vacuum back on. All right, hold on. Let me turn this down a little bit. Can you see on the bottom? Can we turn those lights off? Probably not. Can you guys try the switches in the back? Nope, nothing turns off. All right. Okay, I'm going to just do this one more time. Let the pressure out. Are we set up? Excellent. Thank you, Xander. Just letting the pressure back out. You could see it if you were where I was. Could you see anything on the camera?
A little bit.
Gloria, could you see anything? Nope. Oh, that's good. That's what I needed. That reinforcement. Nope, Professor, can't see a thing. Try again. Okay. All right. So I don't know what I've necessarily done differently here, but we'll give it a try. Okay. It's a little high, but if I turn it down, there you go. Can you see? I'm going to try pulling this up a little bit, see if that maybe changes it. So if you're up close to it, you can see a fountain of plasma coming down the outside. Can you guys see the glass going green? Right? So depending upon the glass, this would, there we go. We can sort of see the, so I'm just going to take these all the way. Oh, we're not getting what we want. There we go. You guys see that? Can you stand out of the way? About that? Can you see? There you go. Can you see all the charge rushing around the glass and inside of it? Maybe if I stand on the back side, you can see a little better. And so this was called Gassiot's Fountain, and this is a fountain of charge running over the glass as if it was just running out on the outside. And so this is one of the amazing demonstrations that we can do with these high voltage power supplies. And we are going to now turn the lights back on. And I'm going to hand this over to Xander, who is going to show you yet another amazing demonstration. This one was invented in, 2021. That's when we first saw it on YouTube. And so Xander, why don't you go ahead and turn your power supply on? And I would like everybody, Gloria, do you know what that thing in front of you is called? Anybody know what it's called? How it works? Ooh, you know how it works? Well, that's pretty cool. Does anybody know what it's called? Plasma ball. Plasma ball. How does it work? By the way, you get credit for the class. So on the inside, there's high voltage, and on the outside, you're grounding it. So there's a voltage going through the globe. Can you show us your globe? I'll show them your globe. Gloria, can you tell me a difference between these two globes?
One is like a different shape than this one.
It is a different shape. Is there anything inside this one?
No.
Is there anything inside that one?
There is.
Ooh, there's the difference, okay? Completely empty globe. I'll hand it over to Xander to explain.
Sure. So what we have here is just a simple oscillator circuit. It oscillates at 10 megahertz. But the main key thing that we're using this for is to produce a magnetic field. Because as you all know from the right-hand rule, when you put a high current through a coil of wire, it'll produce a magnetic field. It's going to be alternating up and down. And what I have here is the seemingly empty glass sphere. What it's actually filled with is a small, not small, but xenon gas, which is typically inert.
All right, now you've turned it on.
So right now it oscillating. There's a magnetic field going through the gas currently. And I'm just going to touch it, play around. We don't see anything happening though, right?
Are you actually touching it or are you faking it?
I'm actually touching it.
Okay, just wanted to make sure.
Moving it around.
Because we've been taught not to believe professors. So, okay.
But we don't have anything happen. And the reason for that is because we don't have any free charges moving on the inside. Because as you know, in a magnetic field, charges will move. But how do we get those charges? And as we saw from our previous demonstrations, one way we can separate charges from a neutral molecule is bring a charged object nearby. So what we did is we separated positive and negative charges, and then those now free charges are moving.
Can we turn the whatever lights we can? No, not those.
And we produce what we like to call streamers, which is very similar to our plasma globe here.
Okay.
They'll follow around my finger. But what's really interesting, get one of these to circle around and sort of bite its own tail.
So can you pick that up just real quick? Take it away. Far away. It's gone. Put it back. Nothing. Can you start it up again? Okay, it's just through induction to get started. All right, so what's your next step?
So in order to get one of these to bite its own tail and sort of form one circular loop of current, we need to strengthen the field. So the way we're going to do that is by putting the glass slightly further
I'll take it up.
into our toroid, our solenoid.
Okay.
All right, I'm going to start the oscillator again. And separate our charges. So we formed a circle.
Can you go up top to get it downward so they can see the donut?
Got one of those streamers to make a complete loop. The charges will continue to move around that loop. Toroid.
And just so we're clear, you can actually, pick it up. Our toroid's in there, right? There we go, it forms again. And do you have a few cool things you want to try? So Xander's an undergraduate researcher in my lab, and this is what they do. They play with things to make them do odd things. That was cool.
So all we're doing is making some adjustments to the oscillator circuit.
Ah.
We get some really interesting behavior out of our toroid.
It actually forms a square. Come on this side. Kind of squarish.
I like to think of it as dancing around.
It's dancing around. And can you make it sing? Don't laugh. Shh. You hear it? Yeah, the microphone. Can any of you hear it? Yeah? Okay. So what's happening is the current is pulsating inside at a few kilohertz, and that's how we're getting that. And this is all made possible by a high voltage power supply, inducing a current. Oh, that was pretty good. Maybe walk around to the other side. There you go. Oh, that's so cool. And you can touch it, I hope.
Yes.
And it goes back to where it was. All right, Xander, I want to thank you very much. Let's give Xander a round of applause for his amazing toroid. All right, we have 2 more demonstrations, and then we'll hit to our finale here. Can we get the lights back up? And so I had this beautiful model of my molecule and my charge. So it turns out that if I create a huge electric field, let's say between these two, I will rip off my little electron. Now this is negatively charged, this is positively charged. If I'm in an electric field, what do these want to do? They want to move. Now, this guy's just going to move, and we're not going to see anything. Okay? Hopefully he's safely there. But the giant molecule is going to move along, and it's going to bump into me. It's going to bump into other molecules, and it's going to actually accelerate molecules in the direction that the big molecule's going in. And we can use this to make an engine. So what we're going to do is we're going to go over here. I have a power supply that works just like our Ruhmkorff coil. And what I've done is I've connected it here. In here. What I have is I have some sharp points, and I have some rounded points. And what's going to happen is it's going to separate. At the very end, you'll see a little bit of glowing, separate the electrons off, and those positive molecules will then be accelerated and bump into other air molecules and create a wind heading out this area. So let's give that a try. And do we have our stick? There we go. You guys see it? You can see right there the wind is blowing it out. And can we see the purple on the tips? Can you turn off the lights real quick in the front? You guys see the purple? Right there, that's a little corona like we saw over there. So we can create a wind. If we can create a wind, can we create an engine? And the answer is yes. So let's turn the lights back on. So what I have here is an ionocraft. It is an airplane powered exclusively by ions. And if you can zoom out, oh, you can see it's a triangle. What we have is we have a thin wire on the top. The key here is you need a sharp point and a dull point. Why? Because the dull point won't let the electrons off because it's smooth, and the sharp point will let them create the corona, so you get a charge that flows across the two. And so we've got a sharp wire, and then we've got a blunt or smooth top here. And we've learned it's really important. This is the wing that directs it down. If you just have a tube, there's nothing getting the air to flow. So if I'm correct, we should be able to launch this aircraft into the air. Almost. All right, let's give it one more time. And there we have, powered completely by high voltage. The Ruhmkorff coil is just inside of here. We get about 20,000 volts happening right there. And I told you there'd be fire. So Xandra says it's best to put it underneath. See that? Can you guys see that wind blowing this? Right? See, there's no wind. There's an incredible wind coming out from underneath this. It's probably going to blow it out. It comes out here. There's no wind there. So that's one way you can see the wind. Let's see if we can do the smoke. It's a little hard underneath. You can see it a little better. All right, so that was our fire. Now are we ready for the explosions? Okay, can we get this one hooked up with the orange cord? And is everything all set for your demo, the coils?
I'll need the cord back, but other than that, yes.
Okay, all right. All right. Everybody in my class has seen this demo. It's okay, it's just as much fun the second time around. I need a knife. We got a knife right there. Okay, I have a microwave here that is plugged in, okay. It's a real microwave. I will let you know that after my class's demonstration, I'm not sure I'm going to use it in my office anymore. It's a little bit wonky. So what do you never put in a microwave? Metal. So we should never take, first off, don't do any of these experiments at home, okay? We should never put metal in, so I'm going to put some metal in the microwave. I think a minute should be good. So, does anybody know what the case of the microwave oven is made out of? Metal. Yes. It's actually just fine to put metal into a microwave. In fact, you'll see microwaves that have metal sheets inside of them. The problem, however, is, we'll look at that in a second. So, metal's okay to put in. Don't do this at home, okay? What you should not put in a microwave is this. A grape. It's exactly correct. So I am slicing the grape in half. I'm going to put the two sides in. Okay. Let's see what happens. See if we'll get a second one out. No, the two grafts have separated. All right. By the way, it's going to be a very hot grape. I've learned this. It's boiling. It's boiling. So it turns out that the wavelength is much smaller inside the grape, and you actually build up a resonance where you're getting a high voltage oscillating between the two sides. And that's why a grape will work, and other fruits won't. If it's too small, it's too big, it doesn't work. That's why the grape works. If you want to do this at home, the trick is to cut one in half, but not all the way, so the skin keeps the two sides together for your demonstration. You can eat the ones you haven't microwaved. Okay. All right. Ouch, 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 ouch. That wasn't kidding. All right, so now what I want to do is I want to play with fire and microwaves. So I told you you can put metal in, but you shouldn't put metal in that's been crumpled up. Why? Because it starts to be on the order of a wavelength, but I don't care. So what I'm going to do is I'm going to stick see if I can get this right. I'm going to stick a match and metal in the microwave. Wait a second. Did you guys see that very well? That was kind of hard to see, wasn't it? Let's try one more grape. Let me do one more grape. That's together. Broke apart. Can't use it. Told you. Okay. Okay. Look, we've only used 30 seconds of the presentation. Come on. Say, not put it in the center. There we go. But that's still kind of hard to see. So, does anybody not from my class have a cell phone on? So what we're going to do is we're going to record a video on the phone of the flame, and then we're going to play it back, okay? Stop me anytime. I'm just kidding. Do not put your phone in the microwave. That is a stupid idea. Instead, what you want to do is drill a hole in the back of your microwave. Just so you guys know, I'm not kidding you. There we go. Can you get the inside of the microwave? Oops. All right, so we've got a hole in the back of the microwave. Now what we're going to do is see if the camera can come back and capture the grape, okay? It's got to work. Can somebody help him with the camera just so he knows? Going a little bit further, going a little bit further. Ooh. I just don't know if that camera will work as well.
You have the webcam if you want to.
I just don't know what we would hook it up to.
Yeah. I'm right again.
Can you go back?
Use the phone.
Oh, yeah, you do your phone and you video the phone. That's how we do it. Okay? So it's okay to put your phone on the outside. Okay, there we go. Oh, sorry, reset it. Oh, isn't that cool? Right at the intersection of the grape is where that voltage is going. All right, awesome. Since we've solved that problem, and the lesson to take away here is a phone is okay on the back if you've drilled a hole through your microwave. And once again, that's very hot. So now I said I wanted to play with a little bit of fire and a little bit of aluminum foil. And so what I'm going to do here is I'm going to strike a match. I'm going to place it in the aluminum foil. I'm going to cover it. Let's see what happens. And I've created a plasma inside. The match heats up the gas, so it gets very hot, and the aluminum foil helps it ignite, and then the electromagnetic field keeps the plasma running in the top. So we can create a freestanding plasma inside your microwave, inside a piece of glass. All right, I think cool. All right, so let's thank our camera crew and our phone people for their time. All right. Okay. Now, Xander, this is for you. Do I have anything else to show you guys while he sets up? And the answer is no. All right, so I will explain. Can we bring out the little guy? Once you plug that in, we'll bring out the little guy. I'll explain the little guy. And Eric, could you give me a hand? Could you just take this away and just set it on the floor? Even in front's fine.
This one?
Oh, hold on. Can't let my uranium glass go.
Do you want both of them on the ground?
Yeah, both of them, please. Thank you. In case you're wondering, you get them on eBay. For some reason, nobody wants uranium in their house. I'm not sure why, but we'll figure that one out. Okay.
We're just doing a static. We're not doing music. Yeah.
That's right. We're just going to do the static, and then we'll do the music. Okay. So, remember I told you a room corp coil was a primary coil, a couple thousand turns. Well, it turns out there was a dude named Tesla. He did not invent the room corp coil, did not invent induction, but he was really good at optimizing these coil ratios. And is the little guy going to stop? Is the little guy going to come over here? That was my hope.
Okay. Yes, yeah.
Well, I thought that was long enough to come over. Come on. Yeah. If it's anybody's birthday, this is available. By the way, I turned 40, in case you're wondering. Thank you. That's a complete lie, but I thank you for going with that. One or two of you probably said, oh, that's fantastic. So thank you for that piece. All right, so there's this dude, Tesla, and he said, you know what? I know how to make these kind of coils. Where did our induction coil go off to? I don't know where it went to, but your ignition coil in your car, it's this. So Tesla did not invent this. Tesla just really optimized it. And so what we have here is, if you can zoom in here, take a look. In the circuit board, we have about 8 to 10 turns, and that's just going to be coupled to a transformer with around 900 turns. Anybody know what this is? It is a toroid. Do you know what it does? It's a capacitor. If I've got an inductor and a capacitor, what do I get? Resonance, okay? That was the big thing that Tesla did, is he added resonance. Others did too, but that's how he made his really nice things. So Xander, are you ready?
Yeah.
So let's just see it make some sparks, okay? Somebody turn down these. Who's ever in the back there? You know the magic one. You don't? Maybe it's me? Nope. Yeah, there it is, okay. All right. So what we're going to do, can we have more power? All right. Very cool. Okay. We don't want to break it just yet. So what's going on is exactly what we saw in these coils. I'm going to get these lights eventually. And ta-da. No, it says back for a reason. There we go. So this is exactly the same as we have here. Now you've noticed, who noticed it made different sounds? So what this is doing, by the way, can you show them, everyone, your custom controller?
Yes.
So the students in my lab, can you come take a look? They downloaded the software for this. They built it. It's got a microprocessor-controlled LCD. It does a 6-channel Tesla coil. Jason, are you here? If he was here, Jason, thank you. He helped make this, and particularly the beautiful box. And what he's doing is he's turning on the coil. He closes the switch, gets current to flow, and then lets it go once. And he does that maybe every millisecond. So that would give us a sound of a kilohertz. If he did it every 2 milliseconds, give us 500 hertz. So he can actually create the spark and make it sound different to us. So if we can make it sound different, Xander, can you do something more fun than just make a spark go in a range? Do you have one just for this one? Oh, yeah, let's just do the bumblebee real quick. Is that one plugged in? Yeah, because you just played it, right? All right, you guys heard this on the way in? Yep, I'm ready. Are you ready?
Oop. Had it set up for the other song.
Oh, sorry. My fault. I did things out of order. Okay, go. All right, you guys saw that on the way in, which was pretty cool. Now, by the way, these sparks are about this long, so maybe we'll call that 10 centimeters, 15 centimeters, maybe we'll call that 300,000 volts. But are we here to see 300,000 volts? What are we here to see? Or I die, right? That's what you're here to see, right? One or the other, not the two. And so, you've probably guessed behind the curtain, we have... And can anyone from my class tell me who this is? This is Dr. Evil Image. If you come to my class, we do puppet shows. You'll learn exactly what happens then. All right, Xander, let's do, should we do a duet first? Or do you want to do a million volts? Let's do a duet first. Okay. So at this point, anyone with asthma or respiratory should leave the room. If you don't have a respiratory issue, you'll be fine. I'm just going to stand on the other side of Xander. Yes. Oh, I'm going to stay away from that one, too. Maybe Xander's is a place to stand. That's a good spot. So thank you guys for the duet. That is amazing. Now, if you're like me, if you're like me, I'd like to see a bigger spark. Would you like to see a bigger spark? Yes. So the safe thing to do would be not to play around with a Tesla coil. So what I'm going to do is I'm just going to turn it. And let's just see. So, by the way, 1,000,000 volts, 30,000 volts per centimeter, 300,000 volts per 10 centimeters. I get 1,000,000 at what, a foot or two? Something like that. All right, so we've got basically, I thought it was a meter. I could have done this wrong, but we've got, I don't know, I'm going to call it 2.5, 3 feet. For safety reasons, that's what I'm going to stick with. All right. Xander, can you see if we can get a 1 meter spark here? And I will stay on this side. Let me just turn all the lights off. Yeah, go for it. Can you do the frequency up? So you got one of the two things promised. The last one we'd like to leave on is, and I'm going to push this a little bit more into the center. We didn't practice this. Whoa! Whoa! That could have been disastrous. I'm just going to push it in the middle. Da-da-dum-dum. Da-da-dum-dum.